We have already had 3 classes on source coding. Hopefully, this will be the 4th class and the last class on source coding. So far, we have done the following topics. We have done introduction, we have seen why we should do source coding, why it is possible to do source coding for most of the practical sources, and then we have classified different source coding techniques, especially desired source coding properties. We have seen that we should have uniquely decodable code, so that we can decode any encoded string uniquely in the destination. And then we have seen that even all uniquely decodable codes are not always instantaneously decodable. So, to have instantaneously decodable code, we should have prefix code, so that no code word is a prefix of another code word. And we have seen so far 2 source coding techniques. One of them is Huffman code. We have seen that it is an optimal code and it is a prefix code. However, we need to have all the probabilities of the source to do Huffman coding. And then we have seen Kraft inequality, which gives us a condition, necessary and sufficient condition for having a code, prefix code of a given set of lengths. So, and then we have seen some properties of optimal codes, how much compression is possible to do for a given source, and we have seen that for getting better compression, it is not always possible to do source coding with individual symbols. So, most of the times we have to combine many symbols together to do block-wise source coding, which will give us better compression. And then we have discussed Shannon-Fano-Elias code, which is which we also saw to be asymptotically optimal, though not optimal symbol-wise. So, we will just go through what we have done so far. We have seen that there are 2 types of source coding techniques, one is lossless and another is lossy. Lossless source coding technique involves no loss of information due to source coding, and in lossy source coding technique there is always some loss of information. So, like source coding techniques, compression techniques like JPEG, MPEG, they involve some loss of information, whereas our file compression techniques in computer like WinZip in Windows or compress in Linux involve no loss of information, because we know that we can recover the file back by using uncompress and such commands. And we have seen that variable length encoding gives advantage, gives compression compared to fixed length coding. Then we have seen these 3 kinds of codes. Singular code has 2 same code words. In this case, all the 4 code words are same. Non-singular code has all the code words different, but still it may not be uniquely decodable once you encode a string. Uniquely decodable code is uniquely decodable string wise, but even then it is not decodable instantaneously, whereas prefix code, where no code word is a prefix of another code word, can be decoded instantaneously. We have seen Huffman coding technique. You first arrange the probabilities in decreasing order and then combine the last 2 probabilities into one, and then assign 0 and 1 to the last 2 probabilities, last 2 symbols, and then we go on doing it and adding bits to the symbols. The Huffman code we have seen is a prefix code, especially the example we have seen is a prefix code. We have not proved that any Huffman code is a prefix code, but anyway we accept that. And Huffman code is optimum. There is, for any random variable, there is no code better than Huffman code. So, that is something very interesting and very nice to have. And Kraft inequality, it gives a necessary and sufficient condition for a prefix code to exist for a given set of lengths. So, if these lengths are given, we know that a prefix code exists with these lengths if and only if this condition is satisfied. So, we have proved necessity and we have proved sufficiency of the Kraft inequality condition. And Kraft inequality, we have seen that we have commented that Kraft inequality also holds for uniquely decodable codes. So, it is not only for prefix codes, but Kraft inequality also gives necessary and sufficient condition for existence of a uniquely decodable code for any set of lengths. And so, from there we argued that if for a given set of lengths there is a uniquely decodable code, there is also a prefix code, because if there is a uniquely decodable code of certain lengths, then Kraft inequality is satisfied. Then if Kraft inequality is satisfied, then there is a prefix code also with those lengths. So we should always go for a prefix code of for whatever lengths are given. And also that equality in Kraft inequality means that all the nodes at the maximum level are exhausted or exhausted by the code words. And we have seen that an optimal code length must be in between these two limits. We know that it is greater than or equal to hx, but this is something interesting and we have proved both the parts. Okay, now we have seen that blockwise source coding gives better compression, and where we combine n symbols together and encode them as a single code word. And then we have seen that by doing blockwise source coding, and as we increase block length n to infinity, we actually asymptotically reach the source coding bound. So we get an average code length tends to hx. Then we have seen that Huffman code, using Huffman code blockwise we can actually achieve source coding theorem, the limit given by source coding theorem on the average code length, because Huffman code is optimal. So L must be in that range between hx and hx plus 1. Then we have seen that Huffman code has some disadvantages, that you have to compute all the probabilities and it cannot be applied to sources with unknown statistics. Then we have seen that another source coding technique called Shannon-Fano-Elias code, where we have first we have taken the cumulative distribution function of the random variable, and then if we want to get the code word for x, we see this jump and we take the halfway between them, take this midpoint and then compute this length of the code word to be this way, and then quantize that binary number to so many bits. So in this case, if it is 6, we take the midpoint, express it in binary representation, so 0 point something. So there are bits after point. So you take only 6 bits out of it, that this Lx, whatever is Lx. So then you take this as a code word after the point, those 6 bits. And if we add 1 to the last bit, we get an interval which has all the numbers, all the code words having this as prefix, because any code word which has this as prefix will represent a binary number which will lie in between these two limits, because it will be less than this. This is obtained from this by adding 1 to this, but all the other code words will have this number as the first 6 bits. So this way we have seen that all the code words, certainly code word for the next symbol will be somewhere here, represent a number here. So this cannot be somewhere inside this. So any code word cannot be a prefix of another code word if we construct the code in this using this technique. So this gives us a prefix code, and we have seen that this code also gives us an average length which is slightly higher than what is possible to get for an optimal code. For optimal code, we know that L is less than or equal to hx plus 1, whereas for this we are guaranteed that average length is less than or equal to hx plus 2. But even this minute increase in the average length does no harm asymptotically. As n tends to infinity, we still achieve hx. Now we are going to do arithmetic coding, which is basically Shannon-Fano-Elias code used for block length, large block length and iterative process, and we will do Gibb-Lempel code or Lempel-Gibb code, which is a tabular coding where probability is not at all explicitly coming into the construction of the code. So that is something different from arithmetic code as well as Huffman code. So we start with the arithmetic code. What is arithmetic code? Arithmetic code is a way to do Shannon-Fano-Elias coding for large block length iteratively. So as symbols come, we keep constructing the code. So we don't receive the whole block and then do coding. So this has several advantages. One is that sequential encoding reduces delay. If we receive the whole block and then do coding, the whole coding starts after we receive that block of symbols. So the encoding delay, the total delay is much more than if you keep doing partially, sequentially the encoding. So also block length n can be increased if we do sequentially without increasing the delay. If we receive the whole block and then encode, then if we increase the block length, we have to receive so much larger than if you take smaller block length, and then so the delay will increase. But if you keep encoding sequentially, the delay will not increase as you increase the block length, because as you get partial. First, if you say receive 4 symbols, you probably have encoded few bits, 3 bits. You know first 3 bits, for example. Then you can transmit those 3 bits, and as you go on receiving more symbols, you can encode more and more bits. So you receive the symbols sequentially, and you parallelly keep encoding the bits. So this reduces the delay, and it is it does not increase as the block length is increasing. So in fact, when we use arithmetic code for file compression, for example, we take the whole file as a single block. So the compression is really maximum. You are taking the maximum possible block length. So because we don't pay in terms of delay there. So it is possible to take the whole block length as a single symbol in such a case. Okay. So we are going to basically do Shannon-Fano-Elias coding for a block of symbols. So we are trying to see if we can do encoding sequentially. So first of all, let us see what is the Shannon-Fano-Elias code for the whole block. Then we will see whether we can do it sequentially. So if we have n symbols and we want to do Shannon-Fano-Elias code, first thing we have to do is we have to draw the cumulative distribution function of that n symbols together. So for the n symbols together, we have to draw cumulative distribution function. So before doing that, we have to first arrange all possible n symbol blocks in sequential order. Because to draw cumulative distribution function, you have to arrange them in a sequential order. Okay. So what is the ordering we should use? For example, if the random variable is binary 0 1, if you combine 2 bits, then you have 0 1 1 0, 0 0 1 1. You have to arrange them in sequential order. So you have to use some kind of order in the blocks. So the most commonly used order is the lexicographic ordering. It is called so because in dictionary that's how it is. That's how the words are arranged. So if you want to arrange 0 0 1 1 1 0 0 1 in sequential order, the most natural is the lexicographic ordering, that is 0 0 0 1 1 0 1 1. So that's how we do. If we have 3 symbols and we want to combine 2 symbols together, 3 possible values and 2 symbols together, then this is the natural ordering, lexicographic ordering. This is similar to alphabetic ordering in a dictionary. Okay. So suppose we have combined that way. We have combined the n symbol values, n length block values in sequential order. Then let us see what will be the cumulative distribution function value at a certain I tuple. Say, here we are taking I number of symbols together. So we will increase I and see what is happening later. But here let us see that for I number of symbols, what will be the value. So this is basically, by the definition of cumulative distribution function, is a summation of all the probability of all the I tuples which come before xi, before or equal to xi. Okay, this is the definition. Now this less than equal to is basically according to the lexicographic ordering. So if you arrange these I tuples, for example, in terms like a dictionary, then all the I tuples which come before that in that ordering, those probabilities you have to add. Now this can be broken into parts. This is, take the I minus 1 number of first I minus 1 blocks, symbols, leave the last one. So probability of that So these things have to be less than this. So this is this probability plus you can say all the yi less than xi probability, this will be yi, this and this. Now this will not be, these two will be yi. So this is the probability that xi yi is less than equal to xi. So if we add these two things, we get fx. Now this can be written as this in terms of conditional probability. This is yi given xi minus 1. So probability that the ith symbol is less than xi, less than equal to xi, given that you have received I minus 1 symbols. This is this probability. Now this can be taken out of this because this is independent of yi. So this comes outside, and this probability is basically the conditional cumulative distribution function evaluated at xi. This is yi. So we get this. Now what does this mean? This means that suppose you compute this function iteratively at I minus 1, after you receive I minus 1, you compute the value of the cumulative distribution function of at that I minus 1 tuple, the value you have received. So you will keep that computed, and then after you receive ith symbol, you will compute the cumulative distribution function of the sequence till ith symbol using the previously computed value. So this thing, this minus 1 actually denotes the I minus 1 tuple just before xi minus 1. Okay. So you have computed this at the after you have received I minus 1 symbols. Now you have got xi also. So what you need to compute, this is also computed before. This does not depend on xi. This basically denotes the I minus 1 symbols, a block of I minus 1 symbols. So that probability also can be computed beforehand, and then newly you have to compute this probability, this cumulative conditional cumulative distribution function. You have to evaluate at xi. So then if you multiply with this and then add with this, you get fx. So you have to newly compute only this much. So what it means is that you need not compute all the probability masses or the complete joint cumulative distribution function, because after you have received xi minus 1 and you have received newly xi, you need not compute f at all the other values. You need to compute at only, suppose xi is 1, then you need to compute the cumulative distribution function value only at that point. So conditional cumulative distribution function at that point. So that is sufficient. So you need not compute the whole probability distribution, which is required for Huffman coding, for example. Okay. So we need not compute the whole probability distribution. And arithmetic coding can tackle sources with correlation first of all, and thus give better computation for source with correlation. This we will not show why, but actually that can be done for any coding with blockwise, any blockwise coding. So that will take advantage of correlation also to some extent. So geometrically, what does it mean to compute the probability distribution iteratively? It means following. You have computed, say, these three values in the I minus 1th iteration. You have received I minus 1 symbols and you have computed these three values. Now as you have received xi, what you are going to do is you are going to compute this f conditional probabilities, these three conditional, this is cumulative distribution function at xi, this is the probability of xi given this conditional, and this is the before xi, what is the cumulative distribution function value. So we will newly compute these three, we need not compute all the other probabilities, cumulative distribution function values here, we need to compute only these three values. Okay. So after you have done that, we need to compress this whole thing inside this. So this point will come here, this point will come here, so this blue part will come somewhere here. So this is basically correspond to multiplying this thing by scaling this thing by pxi minus 1, which we had actually in the computation. We have seen that this needs to be multiplied to this. This corresponds to scaling this part to this much. So this will be scaled to this value, that is this, this point will come here. Similarly, these 2 points will come here, scale down. So, after you have done that, we get these probabilities at the ith state. So, we had these 3 values, now we have these 3 values. We keep doing that. Okay. Now, how do we do the coding? How we do the coding is, we know that in the Shannon-Fano-Elias coding, we know that in the encoded code word, the code word will actually represent a number, binary number, somewhere in this interval, because as we keep increasing I, actually this interval will be smaller and smaller. First you had this interval, then this is scaled down, and you have this much coming inside. So, you have reduced the interval. So, this actually the final code word will lie somewhere inside this interval. It will represent a binary number in this interval somewhere. Okay. At I plus 1 level, you will have a smaller length inside this, smaller interval inside this. So, a binary number inside this will be a code, will be the code word for X, that whole block. Now, if these 2 points have the same few, say these 2 points we express as binary number, both the points. Now, the code word will be somewhere in between. So, if these 2 points have binary expression common for few bits, say first 6 bits, first 7 bits are common in both these numbers, then we know that in between any number will also have the same those 7 bits. Afterwards, it may vary from these 2, but these 2 have the same 7 bits, any number in between that also will have the same 7 bits. So, we know the first 7 bits of the final encoded code word. So, we need not wait for the whole file to come before we encode the first 7 bits. We can encode the first 7 bits at the ith iteration itself. So, that is the advantage, that is the iterative encoding we are talking about. So, to summarize, the final encoded code string will represent a sub interval like this, AB, inside this interval. So, a sub interval is basically, it will be a binary number, and you add 1 to the last bit, you get an interval. So, this binary number will be the code word, but this interval denotes all the numbers of which this is a prefix. Those cannot be code words, because you are constructing a prefix code. So, A will be the binary representation of A will be the code word. Okay. So, we know that. Now, if these 2 have first 3 bits common, as you said, it's first 7 bits common, then A will also have first 7 bits same, those 7 bits. Then we can take those 7 bits as the partial encoding of the final code. Okay. As I increases the interval, this will be narrower and narrower. More and more bits will be common to these 2, because this will be narrower, this interval will be narrower. So, more and more bits will come common. First, for at ith level you have 7 bits common, at the I plus 1th level you may have 9 bits common. So, you can then encode 2 more bits. Okay. So, more and more bits can be encoded as I increases. So, that is the iterative encoding. Okay. Now, how do you compute this conditional probability? We have seen that this is the key to encoding. So, there are some special cases where this computation is easy. For example, for IID source, if you know this probability distribution, then conditioning does not change the distribution. So, for IID source it is easy to compute this. For Markov source it is also easy, because this conditioning is simply conditioned on xi minus 1. Xi depends only on xi minus 1, not on the previous symbols. So, it is easy to compute for these 2 special cases. Now, if we do not know the statistics of the source beforehand, how do you tackle the situation? So, the idea is that as you keep receiving bits or symbols more and more, you keep estimating the probability distribution of the source also, and use that distribution to do your encoding. So, you have received 1 bit, you do not know anything what the distribution is. So, you encode safely, you take that uniform distribution or something. or some a priori distribution you assume, initial distribution, and then as you receive more and more bits, you can estimate the distribution according to some model, and then use that distribution to encode the further symbols that you receive. So, here are some models we can use to estimate the probability distribution. If suppose we have received I minus 1 symbols and we are going to receive the ith symbol, then you can estimate the probability distribution, the conditional distribution of the ith symbol based on what you have received in the following way. This is the Laplace model. Here you basically, suppose this is a binary, suppose this is a mary source, any discrete source. Then you count the number of A's, so you are evaluating the conditional distribution, conditional probability of receiving A at the ith symbol if you have received I minus 1 symbols before. These values you know. So, you count number of A's you have received before, and you count the total number of, so this is FA, the number of A you have received before. This plus 1 by, this is number of B you have received before. Now, B you take all other values except A, all including A and other values. So, this summation FB is basically I minus 1 and then plus the number of symbols here. So, this is a model, this is basically taking a kind of the frequency of A beforehand, previously. So, for example, if the source is binary and you have received I minus 1 bits, you count the number of zeros and number of ones. Number of zeros is suppose 6, number of ones is 7, then you take 6 plus 1 by 6 plus 7 plus 2, 6 plus 1 plus 7 plus 1. So, this will give you the frequency, estimate of frequency. Why are these ones kept here? This is because initially you should not have 0 by 0, because you have, if you have received 0 symbols, when you are taking I equal to 1, you have received 0 symbols. So, both FA, FB, all these are zeros. So, you are taking basically 1 by uniform distribution in such a case. Initially you are assuming uniform distribution. For binary you will assume 0 with probability half, 1 with probability half. So, that is the initial distribution we are taking, and then as we take, if you have received 0 in the first symbol, automatically we weight 0 more, we assume that 0 has higher probability. So, that way we keep estimating the probability. There is another model, Dirichlet model, where you replace 1 by alpha. So, if you take alpha less than 1, you try to estimate the probability faster, but that will have more variation though. This will have more error in the estimate. So, you try to reach to the actual probability faster, but you sacrifice, compromise also something. So, this is a special case of this, as you can see, if alpha is equal to alpha is 1, then you get this. Okay. So, now we take an example of file compression using that using Laplace model. So, we assume that the file is binary, we have two symbols 0, 1, and another symbol which can come is end of file. We do not know when the file will end. So, we assume that every time the file may end with probability something. So, we assume that probability fixed. We take some probability for that, and then except that probability, except for end of file probability at any instant, there is some rest of the probability is divided into 0 and 1. So, at any time the next bit can be end of file, 0 or 1. So, it is not bit, next symbol can be 0, 1 or end of file. So, we take this model. This example is from McKay's book. We take this probability distribution, this model. We assume that at any time the file may end with probability 0.15. So, this is that conditional probability. If you have received anything, whatever you have received, the file may end with probability this at the ith symbol, and then the rest of the probability is 0.85, that is divided between these two, depending on how many A's you have received and how many B's you have received. So, we will actually, these are actually 0 and 1, A and B are actually 0 and 1, but we are denoting by A and B because we will denote the output bits as 0, 1. So, we want to separate, we want to distinguish the input symbols and output symbols, both are binary. So, input we are denoting by AB, output we are denoting by 0, 1. So, 0 may come with some probability, and we are basically counting A in the previous symbols and counting B and then taking this estimate of the probability. So, this is divided between A and B, this probability. Okay, now suppose we have received a file which is a very short file of this content B, 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 A, then file ends. So, now we will see how to do the encoding. First, what should I do? First, you have received nothing. So, you have to compute probability of A, probability of B and probability of end of file. So, we assume the probability of end of file is 0.15, you have received no bits. So, you take equal probability for A and B, this summation is 0.85. Then you have received B, because the file is B, 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 A. So, you have received B, then you compute given B, what is the next symbol, probability of next symbol. So, if you compute according to the previous slide, you will get these probabilities. Similarly, after you have received B, you have received BB, you can compute the probabilities of the third symbol. What is the probability that the third symbol is A? What is the probability that it is B? Similarly, you compute probability of end of file. So, similarly, you compute all these probabilities, conditional probabilities. So, this column is basically probability of A given you have received BB is this, given BBB, what is the probability of A in the next symbol is this. So, similarly compute all this. Okay. Now, so we are drawing here the cumulative distribution function. We will see now how to do the encoding. So, here is the 0 1 range. Now, we have cumulative distribution function, A is less than B and B is less than this, we have assumed. This is the ordering we have taken. Now, the distribution function is, if we take those probabilities, we can see that it will be basically approximately this much length. A is probability 0.425, B is probability 0.425, 1 is end of file is probability 1.15. Okay. Now, we have received B, we know. So, we are interested in this jump. So, are these two intervals having any bit common, any initial bit common, that we have to see. Then we can encode that bit, that is the idea. But we are saying that this number has the first bit 1, because all these numbers have the first bit 1, all these numbers have first bit 0. This is basically 0.5 number. Okay. So, this bit has first bit 1, this bit has this number has first bit 0. So, there is no common bit between these two numbers. So, we cannot decide on the first bit also at this moment after receiving one symbol. So, we receive the next symbol, then we are interested in this interval. The interval has narrowed down to this BB, this part. Now, we have to see whether these two numbers have any bit common. Now, we see that they have one bit common, 0.1, both start with 0.1. So, we can give 1 as output, because 1 is certainly the first bit of the encoded bit string, because the final number code will be somewhere in between this, it will have first bit 1. Similarly, we go on doing it. Now, are there any further bits common to these two? No, because second bit of this is 1, third bit of second bit of this is 0. So, we cannot encode the second bit. So, we receive another symbol now. So, we are magnifying this for convenience of viewing. Now, we have basically this much magnified to this. So, it is 0.11 here, 0.10 here. So, now we receive another symbol, this probability we are interested in this jump, we have received B, B, B. So, we are interested in this much, because they still have no second bit not common. Second bit of this interval is 1, second bit of this interval, this number is 0. So, we cannot encode the second bit still. We have received 3 symbols. So far, we have encoded 1 bit. We receive the fourth symbol now. Now, we are interested in this interval. The interval has narrowed down to this much, because we have received A, B, 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 A. So, now do they have these two numbers have any bit further bits common? Yes, both of them have 0 at the second bit and also 0 at the third bit. So, and also 1 as the fourth bit. Both these numbers have all four of these bits common, because 0.1001 is the first part of all the numbers in between this range. So, these two numbers have the same 4 bits. So, we can encode 3 further bits. Okay, we go on doing it. We have this is the previous page's figure. Now, we keep doing it. We receive again, we divide this into 3 parts, B, 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 A, B and end of file. Now, we receive end of file here. End of file, now these two intervals, do they have any, these two numbers, do they have any common further bits? Yes, they have these further bits, 1, 1, 1 and so 1, 1, 1, 0, 1, end of file 1, 1, 1, 0, 1. There is something missing here, it has to be extended to some more. So, we can encode, if you see carefully, you will see that we can encode further 5 bits. So, this is the encoded, this is the code word, code string. So, this is the final code string, the file ends here. Now, how do we do the decoding? We do exactly similar to encoding. We take this and first bit we receive is 1. So, we take this interval. Now, can we see whether the first symbol was end of file or B? We cannot see, because the number, final number code word is going to be some number here, but it may be in this part or in this part. So, we do not know. So, we cannot still give any output in the decoding. Then we take the second bit 0. So, we see this interval. Do this interval lie in between any symbol here? Yes, it is lying in this B, first of all, this B interval. So, we know that the first symbol must be B, but can we decide on the second symbol? No, because it may be BB or it may be BA, it may be here BA or it may be BB here. So, we do not know the second bit. So, we have one bit output B. Then we receive 1 0 0, another bit, third bit. Now, this again we cannot decode the second bit, the second symbol, because it may be here BB or it may be here BA. So, we receive another bit, we are expanding this here. Now, we are receiving another bit, this 0 1. Now, still yes, we can say that it is now in this BB. BB is divided now here. So, BB starts from here and here, so it is inside that. So, we can decode the second symbol also. So, we keep doing that and we see that as we receive bits, we can also decode. So, final decoded output will be this BBBA end of file. So, we can do encoding and decoding in this sequential manner, that is the most interesting part in arithmetic coding. So, we have basically used the same principle as Shannon-Fano-Elias code. It is basically Shannon-Fano-Elias coding, but in a sequential manner. We have seen how to compute the probability in a sequential manner, and we have used that technique to do arithmetic coding. So, arithmetic coding is basically sequential encoding of encoding in Shannon-Fano-Elias coding. So, we now go to another coding technique called Lempel-Ziv code. So, this is a tabular coding technique. What is done is, at any time a list of substrings previously we have received is maintained. So, we will first we receive 1, we have not received 1 before. So, this is a new substring we have received. So, we keep that in a list. So, we enter 1 as one element of the list. Then we receive suppose 1 0, then 1 1 0 0 1, something like that. So, we have received second bit 1, then we see that 1 is already there. So, we have not received any new substring so far. So, 1 0 we have received next 1, then 0. So, we combine 1 0. So, 1 0 is it there in the list? It is not there. So, we enter that new substring in the list. We keep entering new substrings which is not there in the list. Now, whenever we enter something, that input is discarded, we receive again fresh. So, that is how we construct the list. So, we maintain a list of substrings appeared before. Store the output string from the source in a buffer. So, when we encode when we enter a substring in a list, we also discard that, we actually will encode that and discard that from the buffer. Then we will receive fresh bits and keep it in the buffer, and we will see whether we will keep entering receiving more bits and to check at the same time whether it is there in the list. If it is not there, whenever it is not there, we will encode that and enter that substring in the list. We will see with an example how exactly we do it. So, check if the present string at the buffer is there in the list, spelling strong. Check if the present string at the buffer is there in the list. If yes, then wait for one more symbol to come into the buffer and then go back to step 3. So, whenever we have received a string which is there in the list, so if it is there, then we will receive another bit. If it is still there in the list, then the longer substring, then we will take another bit. So, we will continue this till we receive a substring, we get a substring in the buffer which is not there in the list. So, then what will we do? So, if we have received a substring in the buffer which is not there in the list, then first we will find the substring in the list, that is, we excluding one bit, we know that the rest of the substring is there in the list, because we have got that substring in the list. Then we have received another bit, and then that is not there in the substring. So, if we remove the last bit we have received, we know that that substring is there in the list. So, we see which element in the list is that substring. So, if you remove one bit from the buffer, now you get a substring in the list, you see the index of that. So, we transmit that index, that is the part of the encoding, that is part of the code word. So, what is done? So, in the buffer we have many bits. The last bit, say it is 1, then 0, 1, 0, 1 something. So, we know that this much is there in the list, that is why we received another bit. We took another bit and considered this extra longer substring. Now, this bit we consider later. First, this sequence is there in the list. There is a list here where all these code words are listed, and there is a serial number here 0, 1, 2 this way. So, we see the index of that. So, that index, suppose it is 5, the 5 is part of the code word, encoded code word, and then we add 1 to that. So, 1. Now, 5 of course will not be transmitted this way, 5 will have binary of that. So, we will have 1, 0, 1, then 1. So, we will transmit this as the code word for this. So, we take the index of this in the list and then add 1 to that. That is the code word for us. Okay. So, this is the way we keep doing the encoding. Then we will, once we have encoded, we have got this code word, we will empty the buffer. This buffer will be emptied. So, we have a empty buffer now. Now, we keep receiving fresh bits. Next bit is suppose 1, we get this, next bit is 0. We check when we receive 1, we see whether it is there in the list. It is there, then receive another bit. It is there, 1, 0 is there, then receive another bit. Keep doing it till you receive a sequence which is not there in the list. Then you do the encoding as you did before for the first previous symbol. Okay, so we will take an example now. We suppose we are receiving input, but before we receive any input, we have this list. This is basically the 0th, the first element in that is null, because we have to have something in the list before starting. So, that is the initial state. We have one element there, that is a null element. So, we check, we take the first bit, we have received 1. We see whether 1 is there in this. We see that it is not there. The only element in the list presently is null. So, we have got a string substring which is, this is in the buffer, which is not there in the list. So, what do? We first encode the string which is preceding the last bit. So, that is nothing. So, null. Okay. So, we don't have anything. So, we don't have anything, then we just take 1, that is last bit. So 1 is the output if you received 1, but we have also entered this last bit, whatever is there in the buffer. We forgot to mention in the previous part when we are explaining that when we have this, after encoding, this new string which is not there in the list, this total is entered in the list as a new extra element. So that is entered as a element in the table. Then we receive another bit 0. We check whether 0 is there in the list. We see that it is not there. We have only null and 1. So 0 is not there. So sorry, here the output should have been 0 1 because there was null before 1. There was nothing, actually that is null. So 0 1, and then we have received 0. So 0 is not there in the list. So we see that the previous symbol is basically null, previous bit is null. So null is 0th, so 0, and then the bit is 0. So this is the index 0 and this is the bit 0. This is the extra code word, this is the output so far. So then we have to enter 0 here. So when we enter 0, we have to index it. So 0 1 2, but now we cannot represent the index using 1 bit. So we have to go to 2 bits. So 0 0 0 1 1 0. Okay. So then we receive 1, we see that 1 is there. So we receive another bit 1, again 1. So 1 1 1 1 is not there in the list. So we now start encoding it. So first bit excluding the last bit is 1, 1 is there in the list, that is 0 1. So 0 1 is the index of the substring 1, then 1 is added. So we keep doing that, then 0 1. When you go to the next entry of the list, we have to increase the index to 3 bits because we have 5 symbols, 5 elements in the list now. We keep doing that. Okay. But after we do all this, we see that there is no apparent compression. There are more bits here than here. What is the reason? The reason is that the file is too short. We won't possibly get any compression for too short a file like this using glembl coding. So, and another thing is that 0 and 1 are almost equally likely here. They are almost with same number. So we won't get possibly any compression for that reason also. So if we have a sufficiently long file with unequal distribution of 0 and 1, then we will get compression using this technique. How do you do the decoding? So decoding, we are getting the encoded code word. So we know that so we maintain the same list, we keep constructing the same list as the encoder is keeping. We can guess from what code word we receive. So we keep doing that. First the list has this null, we know that the encoder keeps null first. Then we receive 1, that is the encoded bit stream coming from the source. 1, we know that we have received 1. So 1 means first null, and then so null will be there actually anyway. So first 0 will be there, 0 1. So we know that first bit was 1. So we keep 1. Then we receive 0 0. Okay. So then 0 0. So this must have been 0 because 0 denotes the index of in the list. So you have this null first and then 0 is the next bit. So 0 is the output. So you keep doing that way. So we receive then 0 1 1. So 0 1 is the. So how do you know that how much? So we have received more bits. How do you know how much is the index? Because we know that so far we have so many elements in the list, the index must be so many bits. So we take so many bits as the index and the next bit as the extra bit here. So we take the index, that index, what is the element? You take 1. So 0 1 is the index, we know it is 2 bits now. So we take 1 and then add 1 bit here. So we keep doing it that way. Okay. Now we can do improvement in certain way here. For example, if we have 0 and 1 both in the list, for example we had it here, right? 0 and 1 are both in the list, then we know that 0 and 1 are in the list. Like if both S1, S0 and S1 are in the list, then S can be removed from the list. So, let us see what can be removed here. So 1 1 and 1 0 are both there. So 1 will never be, 1 need not be kept here. So we can put a new element here. So we can minimize the size of the list, and that way we can have less number of bits for index. So that will give us a better compression. We need not keep say 56 bits. Okay. So if we can remove some elements from the list, then we can keep the list smaller, and as a result we need less number of bits to represent the index. So that will give us better compression. So we can, if S is a substring and 0 is the next string, 0 is another, S0 is one string, S1 is one string, both are there, then S substring need not be kept in the list, that can be removed. So if S0 and S are both there and we receive S1 now, okay, we know that last bit need not be transmitted because S0 is there. So last bit cannot be 0, otherwise it will be found in the list. So last bit need not be transmitted if S with 0 and S alone are both there in the list. Okay. And we can limit the size of the list by removing any element which is not used for a long time. So which is the least used element in the list. So there are some comments. Is a universal coding, we can use it for any source statistics, it will adapt itself automatically. Asymptotically optimal for memoryless source, and also Linux, compress in Linux, which we gave an example as example of a lossless coding, uses LZ coding. So we have done, we have seen how to do iterative encoding of Shannon-Fano coding technique, that is arithmetic coding. We have taken an example of arithmetic coding of a file using Laplace model of adapting the probability statistics. So, and we have also done LZ coding, which is not mentioned here, but we have done a tabular coding technique, which is LZ coding, where we do not need the probability explicitly. It will automatically adapt the probability. There is some exercises. This is a string. The exercise is to do Gibb-Lempel coding on this string. Then this is a string. This is McCae's book 6.6 exercise. This is encoded string with basic Gibb-Lempel coding, which we have just described. You do decoding for this. Okay. So we have done all this. So we have completed arithmetic coding in this class, and we have done another source coding technique, Lempel-Gibb coding. This is the end of the source coding. We will have new topics in the next class. So again, these two books are very good books. There are other books on information theory, very popular books, but this book is a very lucidly written book and good for undergraduate. Information theory, inference and learning algorithms. It is available in Indian edition with low cost. So I will encourage you to read this book and solve the exercise there. Thank you. This is the end of the source coding technique class.